Hello everyone, my name is Byron Dossett and I chose to do my end of the semester report on power transmission lines and the power losses associated with them. So, the objectives of this PowerPoint is to discuss what are they for our power transmission lines, why should we use them, how do they work, how are they constructed, and to understand the two losses in power associated with them, which is resistive and corona. So this is a Visio diagram that I created illustrating the progression from raw resource to end user consumption of power. The power is stepped up into high voltage in a transformer and it is distributed throughout power transition lines, which is what this presentation will be about. Transmission line efficiencies are roughly 96 to 98%. But we're going to see how they are that high. And then the power is transformed back down and distributed to end users. And the overall efficiency of this process from raw resource to end user consumption is around 31 to 32%. So, what are high voltage transmission lines? Well, they are long distance high voltage transportation systems of power. They can be AC or DC. Primarily, they are three-phase AC. There are three distinct types: overhead transmission lines, which have voltages of around 69 to 765 kilovolts, sometimes higher, but rarely. There are sub-transmission lines, which are like the power lines you see going across or alongside the road. They vary from 34 to 69 kilovolts. And then there are underground transmission lines, which are actually used in more urban areas, and they are hidden underneath the ground. And on the right, you can see an illustration of the different types of transmission lines. So, why use power transmission lines? Well, they reduce power loss, which increases efficiency. When you increase efficiency, you decrease the cost of power, because more power being generated can be used at the end consumer, ergo decrease power cost. So, how do they work? We know that power is equal to current times voltage. And from Ohm's law, we know that voltage is equal to current times resistance. So, if we substitute Ohm's law for voltage into the top equation, we get a power loss is equal to current squared times resistance. So from this formula, to decrease power loss, we should choose conductors that have a less resistive material, and we should reduce the current, ergo increasing the voltage, and this will decrease our R and our I values respectively. If we take a look to the right, you will see a chart that I created in Excel illustrating two different power lines. Both of them carry the same amount of power, 500 megawatts. Both of them are aluminum. The only difference is that the orange line is a 300 kilovolt line, or a line that was up to 300 kilovolts before high voltage transmission over 100 kilometers. And the blue line, it was up to 600 kilovolts, double that of the orange line. And you can see the vertical part of the graph is power loss in kilowatts. And as we see, the 300 kilovolt line actually experiences 4 times as much power loss as that of the blue line, despite it only being upped in voltage half the amount of the blue line. This demonstrates that power is dissipated much more with higher current lines than that of higher voltage lines. So, part 2 of how they work. Well, we have some components. Pylons are where used to hold the conductors, the wire, at a safe distance above the ground and from each other's wires, so the magnetic fields don't cause any arcing. And then there are insulators, which are made primarily from ceramics. You can see in the top right is a insulator and is intended to prevent electrical connection between the conductor and the pylon, which would then ground the power that is transmitted into the pylon. Very essential. So how are high voltage transmission lines constructed? Well, high voltage transmission lines are constructed over long distances. So the preliminary work is zoning, getting certifications, but then you must tree fell a lot, like all the trees in the path. You must build roads for the trucks and machines that are going to be needed to build them, and then you can need to construct the site facilities in which all the workers are going to be working from. After this, you will begin construction of the foundation of the pylons, the assembly of the pylons, and then hanging of the cables. After everything is complete, visual, mechanical, earth fault, transformer station, and startup tests are performed. After this, and the go-ahead is given and is transformed into the grid, or is connected into the grid, the recultivation, the road removal, and reforestation of the site that was cleared is brought, maintaining a safe distance between the conductors and the forest. Here's an example of a 300-mile transmission line. This is a fictional transmission line, but it shows the general the timeline of a transmission line. You can see that it actually takes the course of about 10 years to construct this line, which is pretty accurate to the estimates given online. Now we must understand the two different types of power losses associated with high voltage transmission lines. First one being resistive losses. So resistive losses come between three main characteristics: the resistivity of the material, the length of the conductor, the cross-sectional area of the conductor, and as you can see below, that is the formula for resistance. You have the resistivity, the length, and the cross-sectional area. You can see the areas at the bottom of the equation. This means that the larger the cross-sectional area, the less resistive losses will be associated with a given conductor. So, our second power loss comes from corona losses. And corona is when the air that surrounds a conductor is ionized. And you can see on the right, it causes this purple hue glow. And typically, the corona effect only occurs on transmission lines that are around 245 kilovolts or higher. You can see pictures online where very high voltage lines will glow in the nighttime, especially around edges and rough places, like around the components. This is because sharp edges and rough edges are more susceptible for arcing due to their nature. So contributors to the corona effect are temperature, humidity, and surface condition of the conductor. So, corona losses are typically around 0.5 kilowatts per kilometer, which doesn't sound that much, but if you have a 100 kilometer line, that's 50 kilowatts that are lost due to the corona loss. So how can we prevent corona discharge? Well, as you can see on the right, that elliptical kind of tubing is called a corona ring, and is meant to deter electricity from sharp edges and points. You can also increase the diameter of cables, which increases or decreases the resistance, which causes less corona discharge, or makes the cable less susceptible to corona discharge. And you can also increase the wires in the cable, which increases the surface area of the cable, which will also make the cable less susceptible to corona discharge. So, in conclusion, power losses in transmission lines are normally around 2 to 4% if constructed well and engineered well. Power losses can be mitigated by increasing the conductor size, increasing in voltage and ergo decreasing current, choosing a proper conductor, and to reduce corona discharge, keeping line voltage below the critical voltage of the air to prevent ionization of the air, and to increase the number of wires in the cable to increase the surface area and decrease the likelihood of corona discharge. That is the end of this presentation. If there's any questions, I'd be happy to answer them. Thank you.